Okay, good morning. It's 8:20 local time, so I'm going to go ahead and begin class. And let me start with announcements. Several important things to say. And for those who are here with us live, if at some point during these announcements you have a question, you can either type in the chat box or unmute and speak directly to us. First, just to remind you, there is a bonus, extra credit, whatever you want to call it, Wiley Plus problem set that is currently available. And it is on chapter 17, problems from chapter 17. You can do those problems and whatever points you earn will just be added on extra to your Wiley Plus total for the semester. Those are due by this Friday evening, 11:59 p.m. So there's a chance for you to do two things: practice with chapter 17 and get a few more Wiley Plus points just to help your total. In terms of the classes coming up for the rest of the week, we have our Thursday class. So you should be expecting two videos, one for the lecture video and then one for the class. And then there'll be class on Friday and there'll be a video for that. So those will be coming soon, those videos. Let me also give you just a quick heads up about something a little bit different. I don't think it's going to cause you any trouble or anything, but I just want to let you know about it. Our department is currently working on a research project in an area called physics education research, where we try to gather data about what kinds of teaching techniques are effective in physics. And one of my colleagues in the department, Professor Storms, is working on a research project and is going to be having a little kind of exercise to do some testing of some teaching materials. And the way we're going to do that is we're going to add on one more homework for this class. The way it's going to work is it will most likely be posted on Blackboard, and it's going to be about a physics concept that has nothing to do with this semester, something completely different. That's the point of this, to test some teaching materials on something you haven't been taught already. And all you have to do is answer the questions. You're not even going to be graded on whether they're right or wrong. And so you're either going to get all the points or none of them. You either just answer the questions or you don't. So all it will cost you is some time. I think maybe half an hour, roughly. That'll be posted soon. So just kind of be aware that that's coming. But it'll be homework points, and it'll be kind of like, well, you just get you get more points. Okay. So that will be coming soon. I'll have more details soon about that. But I just wanted to give you a heads up about that. It's called Physics Education Research. And it will just be some kind of short Q&A. Now, the main thing I want to talk about in terms of announcements is the final exam. I mentioned it briefly at the beginning of Monday's class, so I want to say more about it. So it's, as I mentioned on Monday's class, it's officially scheduled for next Tuesday morning, Tuesday, December 8th. But we're not going to do it in that fix it to that time slot. We're going to do it on a more spread out time scale. Here's how it's going to work. The final exam will be available during the following window of time. Starting Tuesday, December 8th at 7 a.m. Eastern Standard Time, and up until Friday, December 11th at 11:59 p.m. Eastern Standard Time. That's the window in which the exam will be available to you. So you will decide when you want to take it during that window. When you are ready to take it, you will send me an email requesting the final exam. And I will be giving you more information about exactly how you do that request, but you will send me an email saying, hey, Professor Trees, I'm ready to take the final. The final will then be sent to you via email. You will, once you have it, you will have 24 hours to write out your answers, your work, save it as a single PDF, and email that back to me. It won't be done on Blackboard because Blackboard won't let me give you 24 hours for a test. It will only let me give you up to 8 hours, but I want to give you 24 hours. I'm not a big fan of Blackboard, okay? Because I'd rather just do it the way we have been doing it on Blackboard. But Blackboard won't let us do it that way. That's why it's different now. So when you're ready, you send an email requesting the final exam. Once you receive that response, the exam itself, you will have 24 hours to email back to me your work. Okay? It'll be the same rules as the midterms, meaning what can you use? The same resources as the midterms. Our Wiley Plus content and your class notes, just like on the midterm. Can't talk to anybody, absolutely no human being, period. You can't look up anything online other than our Wiley Plus site. Okay? You have to sign your name as well as print your name. The signature is your integrity statement saying, I followed the rules. Okay? Same as the midterm in that regard. A little bit more about the final. Our midterms had 4 problems, as you know. Each midterm had 4 problems. The final exam will have 8 problems. 8 problems. There will be 1 problem from chapter 15, 1 problem from chapter 16, 1 problem from chapter 17. That's 3 problems. The remaining 5 problems will be review from earlier chapters that we have studied this semester. And the chapters we have studied, I'm going to omit chapter 1, that's just about units, chapters 2 through 11. So I will pick 5 problems from that earlier content. And no, I'm not going to tell you which of the 5 chapters out of that I'm going to pick, because I want you to review that material. The final exam is a good chance to go back and review some of the stuff we did earlier, because that may not be so fresh in your mind, but it will help you if it is fresh, okay? Okay, so there will be 8 problems, as I said. I have posted a practice final on Blackboard, like I did on the midterm, so that you can see what the exam is going to be like. And like the practice midterms, in addition to the practice final exam itself, I have posted the answers to the practice final questions. I will do a review session for the final, like I have done for the midterms. I'm going to propose that we do it on Monday, the day before the exam window opens. Monday is what's called, as far as final exam schedule is concerned for us, a reading day. That's a study day. No final exams are allowed to be scheduled on Monday. So you should not have any exams on Monday. It's called a reading day, a study day. So I'm going to schedule us for a review session Monday, December 7th at 1 p.m. Eastern Standard Time. I'll send out a Zoom link. And that's where, like any of the other review sessions, you just ask me questions about problems that you would like to talk about, okay? Okay, so that's what I have for now for the final. You can always ask me questions about anything I've said. If you would like to ask now, you can either type in chat or unmute your audio.
Professor Trees, I wanted to ask something.
Okay, I hear a question. Yes.
So about these bonus homework point physics educational research thing, is it going to happen before or after the exam?
I'm not sure right now. I was under the impression the materials were going to be ready at the beginning of this week, but they aren't. So I'm going to learn this. I'm going to learn at 10 o'clock this morning what the plan is. It's not my research plan. It's another professor's in the department. So I'll be learning later this morning exactly what the time schedule is. it's likely it could go live starting even later today.
All right. So is there a deadline to it?
There probably will be. I don't know what it will be. It will probably be sometime. Well, I don't know if it'll be the end of this week or sometime next week.
Okay. All right.
Okay.
Thank you.
Yeah, I'm thinking it's just going to take you a half an hour.
Okay.
Okay. Okay. Now, don't forget to work on your lab reports for the last experiment, experiment 8, due by Friday. Don't forget also, if you haven't already done so, to please submit the course evaluation. You do that online. You should be getting reminders about that. And with each reminder, it sends you a link. And you just click on that link and it will take you to the evaluation for the course. As of this morning, we were just at about 35% participation. I'd like to get that up closer to 80% if we can. So let me urge you to take a few minutes and fill out the course evaluation. I think you have until Friday to get that done. After that, the program that runs that will shut down and won't let you do it anymore. Okay, any questions about anything I've said during this time? Okay, well, then let's talk about the material for today, the material that goes with the video lecture that I sent already. We are talking about section 2 in chapter 17, traveling sound waves. And let me just remind you, I've got the learning objectives like I always do for class. Let me remind you of kind of the scenario of what we're talking about. Probably the most straightforward thing to visualize for our traveling sound wave, especially in this section, is a long tube filled with air, horizontal tube lined up along the x-axis. And when there's no disturbance, no sound wave in the air tube, then the air is spread out uniformly and is at a pressure that we call atmospheric pressure. And at sea level, that's 1 × 10⁵ Pascal. Pascal is a Newton over meter squared. But we are going to create a sound wave, a longitudinal traveling wave in that air column. And the way we do that is we have at one end of the very long column a tight-fitting piston that we can move back and forth. And if we move that piston back and forth with simple harmonic motion at a frequency that we control, we will create a sinusoidal longitudinal traveling wave in the air. The air is the medium. We have created a sound wave. This is exactly what happens in an organ pipe, for example. And this schematic drawing that I'm showing you is a representation of the traveling sound wave in the pipe. It's a snapshot in time. It's very schematic, of course. And it's showing regions where the air molecules are bunched up. Those are called compressions. They're pushed together closer than normal. And regions where the air molecules are spread out more than normal. Those are called expansions. And that whole structure of alternating compressions and expansions travels in this picture to the right, the plus x direction at speed v. And the picture also shows, so that's showing you the speed of the wave, that the distance between two neighboring compressions is the wavelength lambda. Now, if you zoom in on a parcel of air, an element of the air, how about the element of air that would be resting right there at the origin at x = 0? And if you could watch that parcel or element of air, what would it be doing as the wave propagated down the tube? That parcel of air, that fluid element, would be oscillating back and forth symmetrically about x = 0 with simple harmonic motion. And the lower picture is a zoom in of that, showing you Here's the fluid element. It's kind of shaded purple at this snapshot in time. And when we took this snapshot, that fluid element was displaced to the right from x equals 0, right there. That's where it would be at rest. And it's displaced to the right by that amount s. And it's oscillating in general at a maximum s max to the left and right of the origin. And there's a formula that we want. It's called the wave function that describes that displacement s of the fluid element that would be resting at a certain location x and as a function of time, s of x and t. And it has this form. This is the form your book uses. There's the amplitude, s maximum. Then they use a cosine. You could use cosine or sine. It really doesn't matter. Just be consistent once you pick. Of k times x. Remember, k is called the angular wave number. Plus or minus, because I want to allow for a wave that could travel either plus x or minus x. Omega times t. Omega is called the angular frequency. And you could even have a phase shift, phi. I'll put that in there. And that's the wave function that describes the back and forth oscillation of a fluid element. It's the fluid element that would be resting at location x. So you tell me the x and the t, and I would plug into this formula and tell you the s. How much is that fluid element displaced, left or right, at that time? Okay, we're going to practice with that kind of formula in today's class. But let me show you the other learning objectives. There are several more, and I'm going to focus on the important ones I want us to be able to work with. Out of those listed, one of the most important learning objectives is 17.2.3. Apply the relationships between wave speed v, angular frequency omega, angular wave number k, wavelength lambda, period capital T, and frequency f, all those things. We need to be able to use the very simple but useful relationships that relate those things. So let me write those down here. Okay, I'll start with this one. Angular frequency omega equals angular wave number k times wave speed v. Just want to remember that. You can always check it with the units. Make sure the units are consistent on both sides. Angular frequency omega, you want to remember, is in radian per second. I'm just talking about the units. Angular wave number k is in radian per meter. And of course, wave speed v is in meter per second. So when I combine those units on the right, notice the meter parts there and there cancel, and the units on the right are radian per second, which are the same as the units on the left. That's how you know you've got the relationship right, just that the units are consistent. Now, that equation can also be written as follows. It's the same thing as this. All you do is replace the omega with 2 pi f, f being the regular frequency, and the angular wave number k with 2 pi over lambda, lambda being the wavelength, and you get this handy little formula. The regular frequency f of the wave is equal to the speed v of the wave divided by the wavelength. Very handy. Or, remembering that frequency is 1 over the period of the wave, that's equivalent to that period is equal to the wavelength over the speed. So all of these are essentially the same thing. They really are essentially the same thing, but you need to be aware of all those versions of them because you never know which one might be handy in a given problem. Another learning objective I want us to be aware of, 17.2.5, for any particular time and position, calculate the pressure variation, delta P, measured relative to atmospheric pressure of an element of air as a sound wave travels through its location. So I want to write that down. What's the formula for calculating the pressure variation. Because really the sound wave is two waves. There's a displacement wave, that's the function S of x and t that you see at the top of the screen. And there's a pressure wave, and that's this wave function I'm about to write. Delta P of x and t. It's also a sinusoidal wave like the displacement wave, but it's a quarter cycle out of phase with the displacement wave. So here's what it looks like. There will be an amplitude, a maximum pressure variation, delta P max. And then if we used cosine for the displacement wave up above, then we use sine for the pressure wave. So it'll be sine of kx plus or minus omega t plus phi. And we got to be able to use that formula to calculate delta P. And we will. I'll do that in just a second. But there's one more learning objective I want us to focus on, 17.2.7. Apply the relationship between pressure variation amplitude, delta P max, and displacement amplitude, S max. It turns out you can derive a relationship between those two amplitudes, the amplitude of the displacement wave and the amplitude of the pressure wave. And I talked about that in the lecture video. And if you want to see that derivation, then read section 2 in the book. I'm just telling you the result. The amplitude of the pressure wave, delta P max, is given by a product of three properties of the wave, namely the speed of the wave, v, the volume density rho of the medium that the wave is traveling in, the angular frequency omega of the wave, and then multiply that by the displacement amplitude. It's kind of an odd looking formula, but it's really actually quite helpful for relating the displacement wave amplitude and the pressure wave amplitude. Okay, so what I have to do next is just more practice with these. So let's go first to a warm-up practice. Let me clear up this screen a little bit here, and let me show you what this says. We are given a wave function for a sound wave. Yep, that's the fancy language, wave function for a sound wave. What they mean is this kind of formula right here. This is the same thing as what I just wrote up here, right? Delta P of x and t equals delta P max sine of kx plus or minus omega t plus phi. That's the pressure wave function. We are given that wave function here in this practice, but we're given numbers for the constants. The number out front you can see is 1.50 Pascal. Then there's the sign, and then there's the argument of the sign, sine of. Now the argument might look a bit weird, but this is one way you might often see it in a book. Inside the sign there is pi times 0.9 inverse meters times x minus pi times 315 inverse seconds times t. Okay, well, they're still just giving us constants with units. And no matter how weird it might look at first, the constant multiplying the x, now be careful, that's that. Pi times 0.9 inverse meters, that's k, the angular wave number. K is the constant that multiplies x. And also the constant that multiplies t. Watch out, it's pi times 315 inverse seconds. That is the angular frequency omega. Omega is the constant that multiplies t. So they're just telling you k and omega in a kind of a somewhat different way. But they are telling us the wave function for this, the pressure wave part of this sound wave. Now here come the questions, none of which are going to require a lot of calculation because we're just warming up here. First, what's the pressure amplitude of this wave? Delta P maximum, okay? And really all this practice is trying to get at is, do you understand how to interpret this wave function? There's no calculation for part A. Do you see how you would answer it? The pressure amplitude of the wave? It's that number right out front of the sign. That's the pressure amplitude, delta P max. So the pressure amplitude, delta P max for this sine wave is 1.50 pascals with the units. That's the maximum variation in the pressure above or below atmospheric pressure. Remember, this is a variation with respect to atmospheric pressure. 1.5 pascals above atmospheric to 1.5 pascals below atmospheric. Remember, atmospheric is 1.05 times 10 to the 5 pascals, a little more than 100,000 pascals. We're talking about 1.5 pascal variation on top of that. Very minute. Yet that's what your ear can detect. All right, B. It asks for the frequency of the wave. Now be careful. Be very careful. Frequency. Don't misinterpret what it's asking. It's asking for F, not omega. Don't give me omega. That's a common mistake. If we wanted omega, we would ask for the angular frequency. We want F. Okay, how will we get it? Well, I do know what omega is from the wave function. Omega is pi times 315. So if I know omega, can I get F from that? Yes. Remember, omega equals 2 pi times F. So F is omega divided by 2 pi. And now I'm going to write down the omega from the wave function. I'm going to write it a little differently than the way it's written there. I'm going to write it like this: 315 times pi, and the units of omega are radian per second. They didn't write the radian unit up in the wave function, but it is there. That's the omega. So that goes upstairs. And then I have 2 pi downstairs, and there is actually a radian with that. Remember, radian is a dimensionless unit. Now let's see, there's a pi upstairs and a pi downstairs and a radian, so all that stuff cancels. And F is 315 divided by 2. That's exactly 157.5. What would the unit be? Well, it'd be 1 over second. The convention is when you're talking about that unit in a wave, because you're talking about frequency, you call 1 over a second a hertz. 157.5 cycles per second. That's the frequency. C asks for the wavelength, the repeat distance of the wave. Here, you want to use the fact that you know the angular wave number, k, from the wave function, because k and lambda are related. K equals 2 pi over lambda. So I'll use that to get lambda. Lambda is 2 pi over k. What's your algebra there? Now I'll plug in numbers. 2 pi, it's actually 2 pi radian. K, let me write it like this: 0.9 pi, and the units of K are radian per meter. Now simplify. I've got a pi upstairs and a pi downstairs, a radian and a radian. The unit's going to be meter upstairs, and 2 divided by 0.9, I'll give you 3 sig figs, is 2.22 meters for the wavelength of a sound wave. Okay, it's a relatively long wavelength. D, what is the speed of the wave? Okay, that's just plain old V of the wave. How about using one of those formulas that I mentioned earlier? How about V equals F times lambda? Just rearrange and get V. And then plug in the numbers. F is 157.5 hertz. Lambda is 2.22 meters. Remember, a hertz is a per second, so the units are going to be meters per second, and you multiply that out, and you get 350 meters per second. And if you remember from Monday's video lecture, the speed of sound in air at room temperature is 343 meters per second. So 350 seems reasonable. This presumably then is a sound wave in air of some kind. Okay. All right, now that's just our warm-up practice to make sure that we can work with one of these wave functions. Okay. Any questions on anything I did there? Okay, so now let me do a more standard Wiley plus homework type problem. Okay, we're going to look at a sinusoidal longitudinal traveling wave in air. And I took this one out of your book. It's chapter 17, problem 13 at the end of that chapter. And they're going to tell us a lot of information, a little bit more indirectly than the practice we just did. That was just warm up. So let's read what it says. We have a sound wave of the form. Okay, so they're giving me the wave function for the displacement wave, S of x and t. That's the form of it. S max cosine of kx minus omega t plus phi. It's traveling at 343 meters per second through air in a long horizontal tube. All right, at one instant, air molecule A, or if you like, air parcel A, which would be resting at x equals 2 meters exactly, has been displaced. It has a maximum positive displacement of 6, watch out, nanometers. These displacements of these air parcels is not big. Whereas air molecule B, or air parcel B, that would normally be resting at x equals 2.070 meters, has a positive displacement of 2 nanometers. And all the molecules or parcels between A and B are at intermediate displacements, meaning all the air parcels between parcel A and parcel B have a displacement between 6 nanometers and 2 nanometers. They're telling us information about the structure of this displacement wave. And now they're going to ask us to answer some questions. First thing they want us to do is sketch the displacement function S of x and t at this instant in the region between A and B. Well, we know we need to draw sketches to help us visualize. So let's draw a sketch. This would be a snapshot at time t. And I don't know what the time is, do I? It doesn't say what the instant time value is. It's just some instant. But I have a good bit of information. I'm going to plot S in nanometers, the horizontal displacement, versus X in meters, okay? And I'm going to focus on the region of the x-axis between x equals 2 meters, 2.000, and x equals 2.070. Those are the, if you like, points A and B. And I'm going to start the x-axis reading at 2. You don't have to start at the origin. You don't have to start at 0, I should say. So that point right there, well, I didn't want it to do that. That point right there is going to be x equals 2.000, parcel A. And then I'm going to do tick marks at 0.01. So there's 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07. There is 2.07. That's parcel B. Okay, just using the information they've given me. Now let me go put tick marks on the y-axis. That's the displacement, horizontal displacement in nanometers. Well, one of the displacements is 2 nanometers and the other is 6. So let's do something like 2, 4, 6. Like that. All right, now, how are we going to plot this? It's just a sketch. The air parcel that would be resting at x equals 2.000 meters, parcel A, has been displaced in the positive x direction to the right by an amount s of 6 nanometers. So for x equals 2 meters, s is 6 nanometers. So I'll put a dot, I'll put it in red, right there on the graph. X equals 2 meters, s equals 6 nanometers. The other data point I know is that when x equals 2.070 meters, s is only 2 nanometers. So that's going to be a point right there. And that all the other x values in between have s values between 6 and 2. And it's got to be a sinusoidal wave. So this has got to look basically like a sinusoidal curve. And in fact, it's got to look like a cosine. Okay, dot, dot, dot. Goes on and on. You're just seeing a part of a cosine. That's what they're telling you. They're telling you information about this cosine curve, and you're sketching part of it at a particular snapshot in time, t, although I don't know what the t is. Okay? All right, so the point is to just help us visualize that what we've got is a part of a cosine curve here. Okay, now let's go on to part B. That's our sketch. It asks us to determine the angular wave number k of the wave. Well, it's quite natural for your brain to think about, let's see, angular wave number k is 2 pi over the wavelength. If I knew the wavelength of the wave, I could just use that. The wavelength is the repeat distance of the wave. Unfortunately, what I know is basically what's sketched in that graph. And there's not enough information in that graph to just look at it and deduce what the wavelength is. So we're gonna have to work a little harder than just using that. All right, well, we know we have that wave function. S of x and t equals S max cosine of kx minus omega t plus phi. Let's use that. Here's what we know. For parcel A, okay, for the parcel labeled A, we have maximum displacement. We have maximum positive displacement. Look at the graph. Look at point A. It's at a peak on the cosine curve. That's maximum positive displacement to the right. Okay, S max. We're at S max, which we know is 6 nanometers. Now, how do we get that maximum value of S out of our wave function? Well, the wave function is S max cosine of kx minus omega t plus phi. If my S is equal to S max, the cosine must equal 1. So just the cosine part of k, now I'm going to label the x as x sub a, because that's what we're talking about, that x value, that must equal 1. That's what must be true if parcel A is experiencing a maximum displacement. But wait, if the cosine of an argument, I don't care how complicated the argument is, the blob, if the cosine of a blob equals 1, what do we know about the blob? Well, then the blob, this part, kxa minus omega t plus phi, that's the blob, that's the argument of the cosine. If the cosine of that equals 1, then that must equal 0. Cosine of 0 is 1. Now, if you're really on the ball, you might be thinking, well, there are other possibilities. Yes, it could be 0 here, or it could be any even integer times pi. 2 pi, 4 pi, 6 pi, 8 pi, so forth. And that's true. It could be 0, 2 pi, 4 pi, 6 pi, 8 pi, so forth. You can go through this and check for yourself that if you put instead of a 0 there, an even integer times pi, and then go through the math that I'm about to do, you'll get the same answer I get. In other words, whether I choose that to be a 0 or 2 pi or 4 pi or 6 pi or 8 pi does not affect the answer we're going to get. All right, now I'm going to use that to just rearrange like so. Negative omega t plus phi equals negative kxa. See, I just rearranged it and got negative omega t plus phi by itself. Let me number that, equation 1. That's going to be useful because this bit right here, negative omega t plus phi, I know absolutely nothing about. I don't know the omega of the wave. I don't know what time this snapshot was taken at. I don't know what the phase shift phi is. So eventually, that stuff's going to have to go away. You'll see how it's going to happen here in just a second. Now, what about point B? That's the other point that we know something about. At point B, we know what S is. S at that location, x sub b at time t, is 2 nanometers. For shorthand, I'm just going to denote that S sub b. That's the displacement of the air parcel at point B, 2 nanometers to the right, not 6 nanometers. That was for parcel A, 2 nanometers. So now let me use the wave function again. S of parcel B, S of x sub b comma t, is S max cosine of k times xb minus omega t plus phi. See, I'm using the wave function, but now it's for xb. Notice how I labeled the x, xb. Now what I'm going to do is I'm going to substitute equation 1 right there, so that I don't have to deal with the negative omega t plus phi, because I don't know what it is anyways. So then I have SB equals S max cosine of KXB. Then I have minus omega t plus phi. But from equation 1, minus omega t plus phi is negative KXA. So now let me show you what we're going to do, because now we're kind of over the peak of the hard part. Let me write this as SB equals S max cosine of. Let me factor a K inside there. K times XB minus XA. And let me write XB minus XA as delta X. And I know what that is. XB is 2.070 meters. XA is 2.000 meters. So XB minus XA is 0.070 meters. All right. We're kind of honing in on what we want. We're going to get K out of this, right? We're going to solve this for K. Because the good news is I know every number there but K. I know what the displacement of parcel B is, 2 nanometers. I know what the maximum displacement is, the amplitude, S max, 6 nanometers. And I know delta X, 0.07 meters. So I can solve for K. Let's divide both sides by S max. And then let me take the inverse cosine of both sides and divide by delta X. And you get K equals 1 over delta x times the inverse cosine of SB over S max. And now let's plug in numbers. 1 over delta x is 0.070 meters. And then the inverse cosine of SB, let's write the numbers with their units. SB is 2 nanometers over S max, 6 nanometers. Note the units of nanometers cancel. And I take the inverse cosine of a third. Careful, put your calculator in radian mode, because I need that output to be in radians, because K is in units of radians per meter. So you put your calculator in radian mode, you take the inverse cosine of 1/3, and then you divide that by 0.07. And you get 17.59 radian per meter, which if you round to 3 sig figs, is 17.6 radian per meter. By the way, you can get the wavelength from that if you want. It doesn't ask you to do it, but it's easy. The wavelength is 2 pi over K. You get 0.357 meters, 35.7 centimeters. And look what you did. You took some somewhat cryptic information about a sinusoidal wave, and you've deduced a key property of it. Actually, more than one key property. Its angular wave number, K, and its wavelength. All right, now, what else does it ask us? Oh, one more thing. What is the frequency F of the wave? Okay, now make sure you answer the question as asked. Don't give me omega. If it asks for F, you have to give me F. But I'm going to start with this formula. Omega equals K times V. This is the way I'm going to do it anyways. I'm going to substitute that omega is 2 pi F. So I get that. Then I'm going to divide both sides by 2 pi. That's all I need here. For the angular wave number, let's put in 17.59 radian per meter. I was told the V, 343 meters per second, over 2 pi radian. Radians cancel, meters cancel. The units will be 1 over second, which is called a hertz. And you plug those numbers into your calculator, and you get 960 hertz. Okay? All right, so that's a typical Wiley Plus problem. They're telling you information about a sound wave, in this case, the displacement wave part, and they're asking you to then tell them other information about that wave. There are more things you could be asked here. Since this is air, we know what its density would be at room temperature, 1.21 kilogram per meter cubed. We could ask you, what's the pressure amplitude, delta P max, of the corresponding pressure wave? You might think about how you would get that, because that would be another thing that you could be asked. Okay. Okay, so that's my practice with you with sinusoidal traveling waves. Does anybody want to ask a question about what I just did? So what's coming up for Thursday's class? There'll be a video lecture and then a class video. And we're going to talk about interference, like we did in chapter 16 for waves on a string, but now for sound waves. And then Friday's class, the last class of the semester, we will talk about the Doppler effect. That will be that topic. Okay, so that's all I have for now. And contact me if you have any questions about anything. And otherwise, I'll see everybody on Friday.
Thank you.
You are welcome.
Hey, Professor, can I ask a quick homework question?
You sure can.
So for the chapter 16 Wiley that we just had on Monday,
Okay.
problem 58, it's part B that I have a question on.
All right. I'm looking at it right here. Okay. Let me get a new screen here and let me read. Okay, 1658. So we're given a picture where there's a string tied to a sinusoidal oscillator at point P, running over a support at Q, and it's stretched by a block of mass M. Okay, now I've got numbers here. They're not gonna be the same numbers you had, okay?
Okay.
The separation L, the length between P and Q, is going to be 1.2 meters. The linear density of the string, mu, is 1.6 gram per meter. The oscillator frequency that it's going up and down at, F, is 120 hertz. The amplitude of the motion at P is small enough for that point to be considered a node. And there's also a node at point Q where the string passes over that support. What mass M allows the oscillator to set up the fourth harmonic on the string? And the picture shows a fourth harmonic standing wave. That was part A. But
Yeah.
you said your question was about part B.
Yes.
All right. What standing wave mode, if any, can be set up if M equals 1 kilogram? All right. So I'm probably going to have to kind of work my way through a little bit of A. Let me see. So the picture shows in part A that we have a standing wave in what's called the fourth harmonic.
Mm-hmm.
And the formula for the frequency, F sub n, of a standing wave on a string is n times v over 2L. And the v for a wave on a string, the speed of the wave on a string, is the square root of the tension over the mass per unit length. So I think that's going to be a key formula for me. And I know that I'm supposed to find M, okay? So I know that in part A, I'm in the fourth harmonic, so the n is 4. I'll put in n equals 4. I know what's causing the tension in that string. It's the weight of that mass that's hanging there.
Mm-hmm.
So the tension will be mg, so I'll put that in. So that's the key formula. If you want, you can do that, and leave that as a 2. And let's see, I know mu, I know L, and I know F in part A. So I can just solve this for M, and I'm assuming that's what you did.
Yeah.
Let's see, I will get F sub 4 squared times L squared over 4 times mu over G. I think that's right. Okay, let's see what we get here, because I want to talk about these numbers briefly. Okay, the F I was given was 120 hertz. It's going to go there. The L I was given was 1.2 meters. That's going to go there. G we know, of course. Mu, we have to be careful. I bet I need to convert that to kilogram per meter. 0.0016 kilogram per meter. Okay, so whatever that turns out to be, that's the M. I do want to know what that is. So 120 squared, 1.2 squared, 4 divide 0.0016. So I get 0.846. I'll do one more, 4. So if I round that, 0.846. 0.006 kilograms. Now your numbers were different, so your mass was probably a different value.
Mm-hmm.
But I doubt if it was vastly different from that.
It was only 0.95.
Yeah, because they don't change the numbers much from person to person. Okay, now part B. Okay, we're gonna increase the mass. That's clear. We're gonna increase the mass to 1. At least my value is now 1 kilogram. So that's going to mean more tension, right? More mass means more tension in the string. That means this number right here, of course, is bigger than it was before. And that means all the harmonic frequencies, all the Fs, are larger than what they would have been before. And what I want now is, can I get any standing wave mode at all for this M? Now, the problem I have to note is it has to happen at 120 hertz, because that's what my oscillator is going up and down at. I can't adjust that. So the F is fixed at 120 hertz. The L is fixed at 1.2 meters. The mu is fixed at 0.0016 kilogram per meter. The only thing I have that I can think about being different is the N. So what I'm going to start with is this formula right here. Okay. With the understanding that this frequency is fixed by that oscillator, 120 hertz. This mass is now fixed at 1 kilogram. The mu is fixed. Of course, G is fixed, and the L is fixed. I'm going to solve this formula for N. Okay? And if I get an integer, then that means that particular harmonic can be excited at 120 hertz with the given mass. But if I don't get an integer as an answer, then it's not possible to create a standing wave at 120 hertz with a 1 kilogram mass. Does that make sense?
Gotcha. Okay, so I did the same thing where I tried solving for n and I got 1.9. So because it's not an integer, you're saying,
Right.
okay, awesome.
Okay. Is that good enough, or do you want me to go ahead and finish it?
No, that's fine.
You got the idea.
So when I approach problems like this, I just try to solve for n, and it's just like that. If n is an integer.
That's right.
Okay.
You have to have a standing wave, the n value there has to be an integer.
Gotcha.
Okay.
All right. Thank you so much.
Sure, no problem.
All right. Have a great day.
You too.